All right, this is question 16. So number 16. So we have a kangaroo starts a jump by extending its legs, aiming an acceleration of 28 meters per second squared, 4.6 meters as its legs straighten. So I'm just going to draw the kangaroo like this, like that, and then it straightens its legs out, and so it's on the ground, and this little height here is 0.6 meters. This is what I mean by kind of drawing, like kind of labeling things from the problem. So it accelerates, and we're given the acceleration here as 28 meters per second squared. Okay, and then after its legs fully extended, the kangaroo leaves the ground and rises into the air. So it's moving up, and and then we go like this, and then we have this kangaroo, right? And the kangaroo goes up, and then comes back down, right? So it'll have an initial speed that we may need. It goes all the way up. At the very top, that speed is 0, and then at the bottom it'll be going some speed at the final. We can call it final. I don't know the times for these, so this will be time t equals 0 for this stage. This is kind of phase 2. I'll call this T1, and I'll call this part of it T2, and this time I'll say T equals 0 just for this phase, right? So I'm going to start when he leaves the ground. There's going to be another one here, kind of like you can break this up into kind of 2 phases. There's kind of the initial one, and then there's the kind of the flight. So basically, this is the lift, and this is the flight, and those are two different stages. Okay, and so the first question asks is, what speed does it leave the ground? So basically, what's the final speed that this object has, right? So I want to know a final speed given an acceleration over a distance, right? That's the so we're given an acceleration over in a distance. We're not given we're not given the final speed. We're given an initial speed. All right, so we are given an initial speed, which is 0. It says starts off with a 0. We are given an acceleration, and that's 28 meters per second squared. And we are given a distance of some kind, and I'll call it y because it's a height of 0.6 meters. But we're not given any time, so we're not like so we're not given any kind of time that we have, the time from here to here. Okay, so there is actually a relationship between these. Vf squared minus vi squared is equal to 2a times x. Now again, the letters don't mean much. This is just some distance traveled, right? I could call it h, I could call it d, I could call it x, I could call it y, just whatever. We often use x when it's horizontal, but it doesn't have to be. And since all this motion is vertical, this would be probably better for as a y for that. Acceleration could be, it just depends on what you're dealing with here. So now what we have is we're asked for, so we want to know what that is, and we're not given that, right? So we want that, but we are given the initial speed, we are given the acceleration, and we are given x. So this will be Vf squared is equal to 2 times 28 meters per second squared times 0.6 meters. This gives me, as a value, 2 times 28 times 0.6, 33.6. The units are meters times meters, which is meters squared, over second squared, all right? Which it has to be because it's equal to a speed squared. So now I can take a square root. It's a velocity squared, so we have to take the square root there. And so we get Vf is equal to the square root of this answer. So about 5.8. And the units, the square root of meters squared per second squared, would be meters per second. So by following the units through, I can also check to see that my math actually works. Okay, so this gives me the speed, and the question is, how high does it go? So now we're into phase 2, but this final speed of the lift phase, or kind of we call it phase number 1, right, is the initial speed of the flight, basically in the air, which is phase number 2. All right, so we have the this kind of final speed becomes the initial speed here, and then we just have a flight problem. So these are really two separate problems tied together by the same story, but they really are in a sense two separate problems. Now again, we're asked for how high, but we're given just v0, and this is in the y direction. All right, and so we're given an initial speed. All right. We are also given a final speed because at the top anyway, the final speed is 0. We're given an acceleration of negative 9.8 meters per second squared, and but we're not given a distance, so we're not given a height or a y value or anything like that, right? And we're not given any kind of time. Okay, so what we have though is we have if we're given time and speeds and acceleration are related and then when we saw this before was that acceleration was just the final speed minus the initial speed over the final time minus the initial time. In this case, we're going to set the initial time to 0. The final time is what we might be looking for, and we're given this, and we have some of these. So I'm going to multiply both sides by TF. So my final time, or kind of the time it takes to go here, what I'm calling T1 actually, because we can call them lots of different things. It's just whatever's convenient. And so just recognize that the labeling of the equations is not nearly as important as kind of like here's the definition of acceleration, the change in speed or change in velocity over time. All right, and so the time it takes to go, from some initial speed, 5.8 meters per second, up to 0. All right, so we're going to have multiply both sides by here. So we're going to have say T1 times negative 9.8 meters per second squared is equal to the final speed, which is 0 meters per second, minus the initial speed, which is 5.8 meters per second. When we divide both sides by negative 9.8, and this 0 goes away, we have T1 is equal to 5.8 meters per second. I'll put the negative sign in it to be for complete 9 divided by negative 9.8 meters per second squared. This is going to get me something around 0.58 or so. So 5.8 over 9.8, 5.9, okay? 0.59, sorry, 0.59. Now, it should come out in seconds, right? If it's a time, it should come out in seconds. Now, I'm not just going to guess that it's coming out in seconds. I'm going to check to see that my units work. So I have meters per second over meters per second squared. So what we have, when we have something like that, so if I have meters per second over meters per second squared, I hate things that are in, denominators and denominators are so annoying. So I'm going to multiply the top and the bottom by second squared just to get rid of that denominator. And then what we have is one of these seconds cancels one of these. And so what I end up with here is a meter times the second on the top over a meter. And notice that meters cancels with meters, and that just gives me seconds, so this will be in seconds. So I'm not just guessing that, oh, I have a time, must be in seconds, so I put that down. I check the unit so that way I know that I did the math right. If I goof this up, if I goof up the algebra, I'm much more likely to have swapped the numerator and denominator here, in which case this unit stuff wouldn't work, and it would tell me that I goofed it up. So this is one way that I can use to check. Now, it didn't actually ask me what the time was, all right? It asked me how high it goes, okay? And so I can find out how high it goes by just noting that the displacement. I can do a couple of things. I could go from 0 times T0 up to T1 and then back down to T2. T2 is just going to be twice T1. It's going to be the same amount of time coming up as coming down, so T2 will be equal to T1. So I could start with initial speed here and then go for, this is about 1.2 seconds or so, and then see how fast I'm going or how high, and then figure out how high I go, what the displacement would be after that. Or I can say like the initial speed is the initial speed is what, 5.8 meters per second. 5.8 meters per second times 0.59 seconds plus 1/2 the acceleration meters per second times the time squared. I'm running out of space here, so I'm going to move my paper so that way I can write it a little bit better here. Let me just rewrite that. So the y would be equal to the initial y speed times time plus 1/2 the acceleration in the y direction times time squared. And so this would be equal to 5.8 meters per second times 0.59 seconds plus 1/2 times negative 9.8 meters per second squared times 0.59 seconds squared. And so this would be equal to, so let's just do that, 5.8 times 0.59 plus 0.5 times a negative 9.8 times 0.59 squared. I get 1.72 meters. 1.7, I'll do 1.716 meters. Okay, notice also in the, yeah, there's my poor solar calculator in the dark here. Notice, running off the edge here. Okay, so notice that meters per second times a second becomes a meter, and then I also have meters per second squared times second squared also is a meter, so the units work out. I could also do the following. I could say, all right, the final speed in the y direction squared minus the initial squared is equal to 2 times the acceleration, 9.8 meters per second squared, times the distance that we, again, don't really know. Okay, and the final at the very top of my picture, make sure that I can see it here, yes, at the very top of my picture here is 0, so that would be 0, minus 5.8 meters per second, this whole thing squared, times, it would be equal to 2 times 9.8, negative 9.8 meters per second squared, times x. And I can solve for x. So the minus signs are going to cancel, and so I should end up with 5.8 squared divided by 2 divided by 9.8, and I get exactly the same 1.716 meters. So either one will work. If you don't need to do the time, I thought it asked for the time, so that's why I did that. But if you don't want to do the time, then you can just jump to this. Again, you can make a chart of like, okay, if I'm given, which things am I given and which things am I looking for? And a lot of the problems have kind of a similar structure.